Let's rewind to number 1. Let's start with the Mesopotamians. They imagined a flat, circular Earth enclosed in a cosmic ocean. This was one of the earliest known representations of the universe, and it influenced many subsequent cultures. Meanwhile, in ancient India, the Rig Veda of Hinduism presents a cosmological hymn known as the Nasadiya Sukta. It describes the universe's origin from the Hiranyagarbha, or golden egg. This concept involves cycles of creation and destruction, with the universe manifesting and becoming unmanifest over vast periods, each cycle lasting for 4.32 billion years. Fascinatingly, Hindu cosmology also posits the existence of innumerable universes that coexist simultaneously. Hebrew cosmology depicted a universe with 3 main components: the firmament, Sheol, and Tehom, the abyss. This view aligns with the Mesopotamian idea of a flat earth beneath a solid sky. In Zoroastrian thought, the cosmos is seen as the battleground of a cosmic conflict between existence and non-existence, good and evil, and light and darkness. The Babylonian map of the world illustrates a flat earth surrounded by a cosmic ocean with 7 islands arranged in a 7-pointed star. Similarly, biblical cosmology shares the idea of a flat, circular earth floating on water, topped by a solid firmament to which the stars are attached. Ancient Greek thinkers also made significant contributions. Anaximander introduced a non-mythological model of the universe, proposing a cylindrical Earth floating freely in the center of the infinite cosmos. He described celestial bodies as fire-filled wheels around Earth. Pythagorean cosmology suggested a moving Earth, rotating and orbiting around a central fire, not the Sun, with planets and the Sun also orbiting this central point. This model even included a hypothetical counter-Earth. Plato described the universe in spherical terms, with the Earth at the center, surrounded by celestial bodies arranged in a series of concentric spheres. He introduced a complex cosmology involving the demiurge and cycles of celestial movements. Eudoxus of Cnidus created a geometric model based on concentric spheres to explain planetary movements, influencing later models by Aristotle and others. Aristotle refined this model further, positing a geocentric universe with celestial bodies attached to material crystalline spheres. He also argued for the Earth's spherical shape based on observations of lunar eclipses and other phenomena. Heraclides Ponticus suggested that the Earth rotates on its axis every 24 hours. There are also disputed claims that he proposed a moving Earth model. Aristarchus of Samos was one of the first to propose a heliocentric universe, with the Sun at the center and Earth rotating around it. Eratosthenes calculated the Earth's circumference, and Hipparchus used parallax to estimate the Moon's distance, contributing to a deeper understanding of celestial mechanics. In Hindu texts like the Manusmriti and various Puranas, we find a cyclical concept of time and universe creation, where each cycle lasts for 4.32 billion years, corresponding to a kalpa, day of Brahma. The universe undergoes creation, maintenance, and destruction, followed by periods of dissolution. The texts also speak of innumerable universes created from primal matter. In the 2nd century CE, Jain cosmology envisioned the loka, or universe, as an eternal entity, uncreated and infinite in existence. They depicted the universe in the shape of a human figure, with legs apart and an arm resting on the waist. This form symbolized a universe broad at the top, narrowing in the middle, and expanding once more at the bottom. Moving to the 5th century, Buddhist texts spoke of countless, boundless, and immeasurable worlds in every direction, emphasizing the vastness and complexity of the cosmos. Around the same time, Aryabhata, an Indian mathematician and astronomer, wrote a treatise on the motion of planets, the Sun, and the Moon. He proposed that the Earth rotates on its axis, causing day and night, and described a geocentric universe with celestial bodies following circular and eccentric orbits with epicycles. The Jewish Talmud from the 5th century also delved into cosmological theories, offering arguments for a finite universe. Meanwhile, Martianus Capella described a modified geocentric model, where the Earth remained at the center, circled by the Moon, Sun, 3 planets, and stars. Mercury and Venus, however, orbited the Sun, all within a sphere of fixed stars. In the 6th century, John Philoponus challenged the ancient Greek notion of an infinite universe, proposing instead that the universe is finite in time. The 7th century Quranic verse from chapter 21, verse 30, "Have those who disbelieved not considered that the heavens and the earth were a joined entity, and we separated them?" offered a unique perspective on the creation of the universe. From the 9th to the 12th centuries, Islamic scholars like Al-Kindi, Saadia Gaon, and Al-Ghazali supported the notion of a finite universe and developed logical arguments to reinforce this idea. Fakhr al-Din al-Razi, in the 12th century, rejected Aristotle's earth-centered universe and proposed that there could be more than 1,000 worlds beyond this world. Robert Grosseteste, in the 12th century, described the universe's birth in an explosion and the crystallization of matter. In the 14th century, Jewish astronomer Levi ben Gershon estimated the distance to the outermost orb of the fixed stars to be about 100,000 light-years in modern units. European mathematicians and astronomers like Nicole Oresme developed theories of Earth's rotation, providing logical reasoning, empirical evidence, and mathematical proofs. In 1501, Indian astronomer Nilakantha Somayaji proposed a unique model where planets orbit the Sun, but the Sun itself orbits the Earth. This geo-heliocentric model illustrated the blending of traditional and innovative thinking. Fast forward to 1543, when Nicolaus Copernicus published his groundbreaking work, De Revolutionibus Orbium Coelestium, introducing the heliocentric universe. In 1576, Thomas Digges took Copernicus's model a step further by removing its outer edge and envisioning an unbounded star-filled space. Giordano Bruno, in 1584, proposed a non-hierarchical cosmology that positioned the Copernican solar system as just one of many star systems in an infinite universe. Tycho Brahe, in 1588, introduced the Tychonic system, a blend of Ptolemy's geocentric and Copernicus's heliocentric models. In this geo-heliocentric framework, the Sun and Moon revolved around the Earth, while other planets orbited the Sun. This model bore similarities to Somayaji's earlier proposal, showing the interconnectedness of global thought. By 1600, William Gilbert rejected the concept of a limiting sphere of fixed stars, suggesting instead an infinite universe. In 1609, Galileo Galilei's telescopic observations revealed that the fixed stars were merely a fraction of a much larger universe. When he aimed his telescope at the Milky Way, he discovered it consisted of countless stars, further expanding our cosmic horizons. Johannes Kepler, in 1610, used the dark night sky to argue for a finite universe. His observations of Jupiter's moons revealed that celestial bodies followed the same laws of motion, reinforcing the heliocentric model and establishing the universality of Kepler's laws. In 1659, Christian Huygens made precise measurements of the angular distance between the Sun and Venus, leading to the first absolute measurements of the astronomical unit. By 1672, Jean Richer and Giovanni Domenico Cassini had refined this distance to about 138,370,000 kilometers, a figure that would later be adjusted to the current value of 149,597,870 kilometers. In 1675, Ola Romer's observations of Jupiter's moons allowed him to estimate the speed of light at approximately 227,000 kilometers per second. Isaac Newton's laws, published in 1687, described large-scale motion throughout the universe and introduced the concept of mutual gravitational attraction, suggesting that stars could not be fixed or at rest. The term solar system entered the English language in 1704, thanks to John Locke, who used it to describe the Sun, planets, and comets as a whole. By this time, it was established beyond doubt that planets were other worlds and stars were distant suns, making our solar system a small part of an immense universe. In 1718, Edmund Halley discovered the proper motion of stars, dispelling the notion of fixed stars. 2 years later, he proposed an early form of Olbers' paradox, questioning why the night sky wasn't entirely bright if the universe was infinite. James Bradley, in 1729, discovered the aberration of light, providing proof of Earth's motion around the Sun, and allowing for a more accurate computation of the speed of light, closer to its actual value of about 300,000 kilometers per second. The mid-18th century saw Jean-Philippe de Chasseau further developing Olbers' paradox. By 1755, Immanuel Kant asserted that nebulae were actually galaxies separate from the Milky Way, referring to them as island universes. Charles Messier and Pierre Méchain published the first catalogue of 110 nebulae and star clusters in 1781, aiming to prevent confusion with solar system comets. In 1785, William Herschel proposed a heliocentric model of the universe, placing the Sun at or near the center of what was then thought to be the Milky Way galaxy. Erasmus Darwin, in 1791, penned the first description of a cyclical expanding and contracting universe. 5 years later, Pierre Laplace restated the nebula hypothesis for the formation of the solar system, from a spinning nebula of gas and dust. The early 19th century brought significant advancements as Thomas Henderson, Friedrich Bessel, and Otto Struve measured the parallax of nearby stars, marking the first measurements of distances outside the solar system. In 1842, Christian Doppler proposed the redshift and blueshift effects, later independently discovered in electromagnetic waves by Hippolyte Fizeau in 1848. Edgar Allan Poe, in the same year, offered the first correct solution to Olbers's paradox and suggested the expansion and collapse of the universe. The 1860s saw William Huggins develop astronomical spectroscopy, revealing that the Orion Nebula was mostly gas, while the Andromeda Nebula was dominated by stars. In 1862, Father Angelo Secchi determined that the Sun was also a star by analyzing its spectroscopic signature. The Michelson-Morley experiment of 1887 aimed to measure Earth's motion through the assumed stationary luminiferous ether, but found no results, ending the centuries-old idea of the ether. The earliest known photograph of the Great Andromeda Nebula, taken by Isaac Roberts in 1899, marked the beginning of a new era in astronomical observation. By 1904, Ernest Rutherford had argued that radioactive decay released heat, providing the unknown energy source that William Thomson had speculated about. In 1905, Albert Einstein published his special theory of relativity, fundamentally altering our concepts of space and time and demonstrating that mass and energy are interchangeable. Henrietta Leavitt's 1912 discovery of the period luminosity law for Cepheid variable stars became a crucial step in measuring distances to other galaxies. The following year, Niels Bohr's model of the atom definitively established the quantum mechanical behavior of matter. In 1915, Robert Innes discovered Proxima Centauri, the closest star to Earth after the Sun. That same year, Einstein published his general theory of relativity, showing that an energy density warps spacetime. Willem de Sitter's 1917 derivation of an isotropic static cosmology and an empty expanding cosmology introduced the concept of a de Sitter universe. Harlow Shapley's work on globular clusters in 1918 showed that heliocentrism was incorrect, replacing it with galactocentrism. A year later, Arthur Stanley Eddington used a solar eclipse to successfully test Einstein's general theory of relativity. The Shapley-Curtis debate of 1920 at the Smithsonian, followed by the National Research Council's publication in 1921, finally recognized galaxies as objects beyond the Milky Way. Vesto Slipher summarized his findings on the systematic redshifts of spiral nebulae in 1922, and Alexander Friedmann suggested a general expansion of space. Edwin Hubble's 1923 measurements of distances to nearby galaxies, including the Andromeda Galaxy, placed them far outside the Milky Way, implying an immense universe filled with thousands of galaxies. Louis de Broglie's 1924 assertion that moderately accelerated electrons must show an associated wave was later confirmed by the Davison-Germer experiment in 1927. Georges Lemaitre's 1927 discussion of an expanding universe governed by Einstein's equations predicted the distance redshift relation, which was further developed by Edwin Hubble in 1929. In 1932, Carl Gunther Jansky's recognition of extrasolar radio signals from Sagittarius marked the birth of radio astronomy. Edward Milne's 1933 formalization of the cosmological principle and Fritz Zwicky's identification of dark matter in the Coma cluster of galaxies laid the groundwork for modern cosmology. Georges Lemaitre's 1934 interpretation of the cosmological constant as vacuum energy and Hans Better's 1938 calculations of nuclear reactions powering stars further expanded our understanding of the universe. Paul Dirac's large numbers hypothesis in 1938 suggested that the gravitational constant might be decreasing slowly with time. The year 1948 saw Ralph Alpher, Hans Bethe, and George Gamow examine element synthesis in an expanding universe, and Hermann Bondi, Thomas Gold, and Fred Hoyle proposed steady-state cosmologies. George Gamow's prediction of the cosmic microwave background radiation in 1948, and Fred Hoyle's coining of the term Big Bang in 1950, highlighted the dramatic shift from the steady-state model to the Big Bang theory. In 1961, Robert Dicker made a groundbreaking argument that carbon-based life can only arise when the gravitational force is small, laying the foundation for the weak anthropic principle. Just 2 years later, in 1963, Martin Schmidt discovered the first quasar, providing a probe into the universe back to substantial redshifts. The late 1960s saw a flurry of discoveries. Stephen Hawking and George Ellis showed that any plausible general relativistic cosmology is singular, and James Peebles demonstrated that the hot Big Bang predicts the correct helium abundance. In 1967, Andrei Sakharov presented the requirements for baryogenesis, introducing the concept of baryon asymmetry in the universe. Following this, Vera Rubin and Kent Ford's 1970 measurements of spiral galaxy rotation curves provided compelling evidence for the existence of dark matter. The 1970s and 1980s brought even more transformative discoveries. Alan Guth and Alexei Starobinsky independently proposed the inflationary Big Bang universe in 1980, offering a solution to the horizon and flatness problems. In 1982, several groups, including James Peebles and George Blumenthal, proposed that the universe is dominated by cold, dark matter. The first large computer simulations of cosmic structure formation ran by Davis, Evstathiou, Frenk, and White between 1983 and 1987 showed that cold, dark matter produces a reasonable match to observations. 2001 marked a significant milestone with the 2DF Galaxy Redshift survey by an Australian-British team, providing robust evidence that the matter density is near 25% of the critical density. This discovery, combined with the cosmic microwave background results, offered independent evidence for a cosmological constant or similar dark energy. In 2002, the Cosmic Background Imager in Chile captured images of the CMB with unprecedented angular resolution, revealing the anisotropy spectrum up to L-3000 and a slight excess in power at high resolutions, known as the CBI excess. NASA's Wilkinson Microwave Anisotropy Probe in 2003 provided detailed full-sky images of the CMB, indicating that the universe is 13.7 billion years old with remarkable precision, supporting the lambda CDM model and inflationary predictions. The same year, the Sloan Great Wall, a massive cosmic structure, was discovered, further expanding our understanding of the universe's large-scale structure. In 2004, the degree angular scale interferometer first obtained the E-mode polarization spectrum of the CMB, and Voyager 1 sent back data from within the solar system's heliosheath, providing invaluable insights into our cosmic neighborhood. The Sloan Digital Sky Survey and 2DF Redshift surveys in 2005 detected the baryon acoustic oscillation feature in the galaxy distribution, a crucial prediction of cold dark matter models. WMAP's 3-year results released in 2006 confirmed previous analyses and included polarization data, further cementing our understanding of the universe's early conditions. Between 2009 and 2013, the European Space Agency's Planck Observatory mapped the CMB's anisotropies with increased sensitivity, providing a clearer picture of the universe's infancy. Improved measurements from WMAP, new supernova surveys, and baryon acoustic oscillations between 2006 and 2011 consistently supported the standard lambda CDM model. In 2014, the BICEP2 collaboration announced the detection of inflationary gravitational waves in the B-mode power spectrum. Although subsequent analysis lowered confidence in these findings, it sparked significant interest in cosmic inflation. The LIGO Scientific Collaboration and Virgo Collaboration's 2016 announcement of direct gravitational wave detection from a black hole merger opened a new chapter in astrophysics, establishing gravitational wave astronomy. In 2019, the Event Horizon Telescope Collaboration published the first image of a black hole at the center of the M87 galaxy, providing visual confirmation of black holes and supporting Einstein's general theory of relativity. Physicist Lucas Lombrizer proposed a vast bubble surrounding our galaxy to reconcile differing Hubble constant measurements, while others suggested the universe's expansion is not uniform in all directions, challenging the isotropy hypothesis. Additionally, verifications from 2011 to 2014 indicated a spatial variation in the fine structure constant, implying potential directionality in natural constants, which could revolutionize our understanding of the universe's habitability. In conclusion, the journey through time and the evolution of cosmological theories have shown us the vastness and complexity of our universe. From ancient beliefs to modern scientific discoveries, each era has contributed to our understanding of the cosmos.